while my assistant is getting ready, let me say a few words. He is faithful, if not necessarily beautiful. So still continuing with the theme of young people, but young at heart, here I am. I see my assistant is ready, so let's go. So this is the obligatory zero origin indexing slide. In addition, for this application, we require that comparison tolerance is 0, because certain functions, in particular, index off on tables and inverted tables is a difficult problem. It can be handled using the talk in last year's user meeting called index off on multiple floats. But it's kind of complicated and beyond the scope of this talk. So here we assume quad CT is 0. So what are we talking about? On the left, we have a table, and on the right, we have the equivalent or an equivalent inverted table. So an informal description of a table is that it's a two-dimensional array in which the items of a column have the same data type. So going down the column, you see that it has the same data type. Another column, and then another column. So this table has 8 rows and 5 columns, and so does this inverted table. And an inverted table is a table in which the columns are nested simple arrays. I'll have a more formal description of what an inverted table is later on in the presentation. And application of comma bar each on an inverted table makes its display more agreeable. Sometimes, and in particular in this presentation, we call a table a verted table to more clearly distinguish it from an inverted table. So X is a verted table, and T is an inverted table. So how do you create these things? A verted table can be created by repeated application of comma bar assign. And an inverted table can be created by repeated application of comma bar each assign. So the tables that you saw in the previous slide can be created as here. At this point, I have a few puzzles for certain members of the audience here. For you array notation gurus, the puzzle is how you create the or specify an inverted table using your array notation without first creating a verted table and then inverting it, and without messing with the readability of the presentation as here. Okay, and there's a second puzzle for you APL2 gurus. APL2 is very proud of its treatment of prototypes. So the puzzle is, how do you get the prototypes of these tables, both the verted table and the inverted table? As far as resource consumption, there's a big difference between a verted table and an inverted table. So I've created XX is a random verted table, and TT is a random inverted table. 20,000 rows, 5 columns. And there's an almost order of magnitude difference in the size, that is the number of bytes required. How about for time? So the first, you can think of the first two as things you might do in a query. And the third benchmark is on index of. Oops. Yeah. There's a IBeam function, IBeam, which computes index of on inverted tables. I'll have more about that later in the presentation. So in the first benchmark, you win big for an inverted table. You still win in the other two benchmarks. But there are some things which is faster for a verted table. But it's a good trade-off because the times involved are really tiny, whereas for the more expensive functions, the inverted table is much faster. Okay, more benchmarks. Unfortunately, it's not all good regarding time, but we can fix that. So these benchmarks are on adding a new record to a verted table on the left and an inverted table on the right. See that, I have to write my own timer because I need to do it a fixed number of times, whereas CMPX, the standard benchmark function, can decide to do it a unpredictable number of times. So in all cases, it's doing the expression 1,000 times each. That's the default. So you see that for a verted table, it's quite a bit faster to add a new record than adding a new record to an inverted table. But from the second, if you compare this to this and then this to this, you know that there's a Dyalog APL has special code for doing comma bar assign, but not yet for comma bar each assign. So I have filed a Mantis RFE on this issue. So why is there such a big difference in space and time for a verted table and an inverted table? Now, In yesterday's presentation by Martin Thompson, Charles Brenner asked a question which, if I may paraphrase, is that is the information in the rectangles all the way down presentation, is that information for implementers or for application writers? And the answer is yes. So I'll show you. I see that my faithful assistant has adapted the slides for the, or customized the slide for the location. We are on the Emerald Isle, after all. Anyway, a basic thing to know about APL systems is that everything's an array, and each array has a header and then the raveled data. So this shows the internal representation for a verded table. So I didn't show the header for X itself. And for a nested array, which X is, the items are pointers, and each pointer points to an array. And each of these arrays have a header and then its data, okay? And then it goes down here. So I've only shown the first two rows of the verded table. And each of those headers take up space. And this function is equivalent to what quad size would give you for simple arrays. And the part in blue shows you the number of bytes for the header, a fixed 24 bytes, and then 8 bytes for each element of the shape. And this is for 64-bit systems. So if a table is verded, then you have a 64-bit or 8-byte pointer for each item, plus whatever it points to, which has a header and then the data. So where's the space going? You know, the pointers themselves, and then the header, and then the data. So for example, for the number 2, you have a 8-byte pointer here, and then a 24-byte header here, and then the data. I'm glossing over some details because Dyalog does some optimization for commonly occurring arrays. So this, and this diagram also explains the time difference, because to access an actual data item, you have to go through the pointer, and then before getting to the data, and you have to do it for each, chase the pointer for each item. And as well, the data are scattered all over memory. Right, so there's nothing to say that this MIF is close to where that join is, or 2 or 23 or 1.25. So this hopefully helps you develop what Martin Thompson referred to as a mechanical sympathy for what's involved in the inside the interpreter for a verded table. Now, compaction, despite the name, doesn't help with this as far as making the data near each other. So possibly it would be useful to have an I-beam function that does compaction on a nested array in general, and maybe something slightly different for a verded table. Next. So in contrast, this is the internal representation for an inverted table. As you can see, there are many fewer pointers, just one per column, and there are many fewer headers, one per column. And the data are contiguous. So the rest of this presentation will be talking about utilities. One thing to say is that if your table has key columns, probably you want to apply the utilities to just the key columns and not to the entire table. Okay, the first one, an important one, is an assertion which tells you whether the argument is an inverted table or not. And if it's not, it stops at the first place where it finds things are objectionable. So this is saying that an inverted table is a non-empty vector of simple array items having equal tallies. Next is one to do indexing on inverted tables. And now, next one is index off. You can do this in APL by as follows. For each column, we place the data item by its index in the principal argument. And then if you mix that and transpose it, you get a matrix of integers. So do that for the left argument as well as for the principal argument. And then just do the ordinary index off. That's that there. And this is what you get if you collect the code together. So it works. Whoops. There is a faster one. It's the I-beam that we saw earlier. Now, despite appearances, the number H is not a random number. It stands for IIX, in Roman numerals, and then that stands for inverted index of. It's something of a sport among Dyalog interpreter implementers to think of ingenious explanations for the numeric constant used in I-beam functions. So as you can see, the I-beam function, TIX, is faster than the APL function, TIX1, and it's also faster than the primitive index of on a verted table. That's the XX iota XX, which is as fast as it is because the interpreter, when doing the primitive iota, looks for a verted table and uses a faster algorithm for it. We realize that some of our users, big users, have lots of verted tables and they have a large code base. They can't easily change all their tables to inverted tables. So we, made a special effort to help them to do index of on verted tables. Aren't we nice guys? And so the last benchmark shows you what can happen So QQ is a general nested matrix. It's almost the same as XX, but the assignment of 34 to row 9999 makes it not a verted table, and then you can see the time difference. Okay. Now, once you have index off in hand, the associated function of membership without unique and even key can be easily defined. So, if you're doing what Eric Wallace was talking about, code audit, is that what it's called? Audit? This is not a lot of code to audit. Now, grade and sort. One way to find grade is as follows. You start with the identity permutation, and then you proceed from right to left. That's what that slash is doing. I should tell my assistant that he should have used slash bar instead of slash, although it doesn't matter in this case. And so, proceeding from right to left, working on each column of the inverted table in turn, you derive the next permutation by grading the permutation of the current column until you get to the end, and then that's your answer. An alternative computation is to replace, for each column, replace each major cell by its ranking, taking care to assign the same ranking to equal items. You mix that, transpose it, you get a matrix of small integers, and then you just grade that. Grade and sort can be packaged together as one function named order here. So order, when you apply it monadically, grades the inverted table argument, and applied dyadically, it orders the left argument according to the grade of the right argument. So in the case where the left and right arguments are the same, you just sort. Now, if you don't like the quadrant C in the definition of order, the definition of order can be made more elegant if there's a dyadic operator which can yoke together the monadic and dyadic cases of the derived function. Yeah. Oops, what happened? Finally, these are the definitions used in the presentation. Okay, thank you very much.
Thank you very much, Roger.